Okay, so let's talk about administrative stuff first. So we have our last homework due Friday, right? That's homework 8. I think the PDF might possibly say homework 7 at the top if you take a close look at it, because it was a copy. Anyway, so the PDF probably says homework 7. That's officially homework 8. So let's do this Friday. You can use a late on it if you want. You can use a late if you want, if you have any lates remaining. Lab 5 is out, both versions. The 4670, the 5670 versions are slightly different. What's common to them is the standard compliant part. The non-standard compliant part's different. 5670 is over radios that we got set up just before Thanksgiving. The 4670 thing is just over the regular comm cloud we've been using. So, so that's due, it's considered a final project, so that's due at our final project due date. It's given to me by the university, so Monday, December 11th, 4:30 p.m. During recitation, or I guess it's officially called a discussion for this class on Friday, we won't have any prepared content. It'll just be extra office hours for Lab 5 or for the homework if you want to talk about that. Umair and I will need to decide which of us is covering that, but at least one of us will be there to talk about whatever you want to talk about. In the past, it's usually like, Lab 5 people want to talk about, but whatever you want to talk about is fine. In particular, we can talk about like ways of extending your Lab 4 or the standard compliant design for Lab 5. So how do you kind of push the data rate? What things can you add to the standard compliant design to push the rate up, or the figure of merit up? Okay, so that's that. We owe you some stuff for grading. The grader plans to get like the last 3 homeworks graded by Thursday. I don't know if we'll have Labs 3 and 4 both graded by Thursday. I'll work on it. We'll definitely get them back before, well before Lab 5 is due, so you can look at them before you submit your Lab 5. And that's all I have. Any questions? Yes?
Are there any office hours, I guess, really for those of us taking the...
Yeah, so we'll have, for Lab 5 also, so we have a regular office hour schedule through Friday, and then we will announce kind of a different office hours schedule for the week after. Until stuff's due, we'll have office hours until everyone's done with everything, the final, the exams, or the projects and everything. It will not in general follow the office hour schedule we've been following during the semester, but we'll announce something. So remind me if I forget. Sometimes I walk out of the last class on Thursday and great, I'm done. I forget to do stuff like that. So remind me, but we will definitely have office hours after this Friday to help with Lab 5 and the final and whatever else. Other questions? Did you have a good break? Who left town? I'm just curious, like what fraction of people? Oh, okay, a lot, yeah. All right, good. Okay, so I didn't. So, okay. So I'd like to talk about wireless channels. And I have kind of like, a message or a punchline to get across on wireless channels. I've been going quite slow this semester compared to previous semesters. We're like 3 lectures behind last semester's pace, I think. Maybe 2. So I think it's because it's kind of more interactive this year than it's been in prior years, which is good, but it also means that we're in danger of not making it to the basic punchline of wireless. So I'm going to try to get the basic punchline across between this lecture and Thursday. You might find me going a little bit faster than normal, but that's intentional to make sure we kind of get the main idea across. So we said there are like 4 ways in which wireless channels are different from comm cloud, right? So passband instead of baseband, filters more aggressively or can filter more aggressively, varies more quickly, okay, and SNRs are lower. Okay, passband we dealt with. That's easy. That arguably makes things easier rather than harder. For the middle 2, the fact the channel filters more severely and that it changes more quickly, I mentioned there's no one-size-fits-all solution to that. Okay, there's not like one technique I can show you that works for all wireless channels to combat those problems. People kind of classify wireless channels into different groups, okay, and then the solution used kind of depends on which group your channel is in, okay. So there are like 3 axes along which people classify these channels. So the first one is flat versus frequency selective fading. So you say it has flat fading if its impulse response is just a delayed scaled impulse, in which case the discrete time Fourier transform of the impulse response will just be flat. Otherwise, if it's not this, then you'll end up with the magnitude of the transfer function varying with frequency. So it's like it selectively fades certain frequencies more than others. That's where the term comes from. And we gave kind of a physicsy interpretation of this. So, the continuous time impulse response. So flat versus frequency selective is defined in terms of the discrete time impulse response. Okay. If you look at the underlying continuous time impulse response, okay, before you sample, if you send an impulse, you tend to get a train of impulses at the receiver just due to reflections. Okay. And you can define a delay spread, which is like the time between when the energy from the shortest path arrives compared to when the energy from the longest path arises. They call it the delay spread. Okay, so just the the maximum delay minus the minimum delay. Okay, you can show, just as like a rule of thumb, kind of an engineering definition, that the channel will be will have flat fading if the delay spread is much less than the sampling rate or the sampling period, and it'll be frequency selective if the delay spread is much bigger than that. Okay, and the idea is like the channel's kind of sampling at rate f. Okay, and if it's sampling really slowly, then it can't really perceive these minute differences among these delays. They all kind of just act as one. Whereas if you're sampling really fast, okay, then you can actually perceive these different impulses. Okay, so that's one classification: flat versus frequency selective. In our terminology in this class, up to this point, we would call this like non-ISI channel versus ISI channel, or a channel with no ISI versus a channel with ISI. Okay, but in wireless, the terminology is slightly different. Okay, another axis is overspread versus underspread. So people use this terminology coherence time in wireless channels, the time over which the channel is constant. Okay, so the coherence time for a COM cloud would be maybe like a couple seconds. It's the time until the clock skew starts to bite you, assuming you're sampling at 44.1 kilohertz. In wireless, this tends to be a lot shorter, or can be a lot shorter. Okay, they define a channel to be underspread if the coherence time is much bigger than the delay spread, and overspread if it's the other way around. And if they're comparable, I don't know, maybe it's neither one or the other. It has elements of both. Okay, so overspread channels are like extremely difficult to work with. Okay, because like the time constant over which the channel remains fixed, like constant, that's significantly less than the time it takes for the channel to finish its response to an impulse. So it's like there's no hope of like learning this channel through simple training, because like the moment you get the training, like it's instantly out of date, it's instantly stale, okay? Because the channel's changed in the time it takes to just finish responding to an impulse. So these are pretty nasty. We're not going to talk about them anymore in this class. We're going to focus on underspread, but you should know that classification is there. And the last one is fast versus slow fading. Okay, so the channel has fast fading. Okay, if the coherence time is much less than what we call the delay constraint or the latency constraint. Okay, so this is the time between when a bit enters the encoder and when it needs to exit the receiver. I can just say encoder and decoder. The time between when it enters the encoder and must exit the decoder. Okay, so for many applications like email and so on, like, the delay constraint is essentially infinity. You have, for all practical purposes, it's extremely long, right? In other cases like, voice telephony, people have measured this and found that it's maybe about 100 milliseconds. You have about 100 milliseconds between when a bit enters the encoder and when it exits the decoder. And if it's any longer than that, then it's hard to sustain the conversation because the delay is just too long. Okay, and slow fading if it's the other way around. The coherence time is much bigger than the delay constraint. Okay, so this third one's different from the other two in that it's not really intrinsic to the channel. Okay, you can't tell whether a channel, if I just describe the physics of a channel, okay, you can just determine whether it's flat or frequency selective from just the physical considerations. Likewise, if it's underspread or overspread, although I guess that depends to some extent on whether things are moving, how fast they're moving, and so on, which is maybe separate from the channel itself. This is totally not intrinsic to the channel, though. This depends on the application. Okay, so a channel can be fast fading if you're sending like email, and then slow fading if you're trying to do voice over it. Okay, so it depends on the application, so it's not so intrinsic. Okay, so like all 8 kinds, you have 3 axes, right, and like 2 possibilities for each axis. So you have 8 possibilities. In principle, all 8 possibilities are possible. In practice, certain combinations are going to be a lot more common than others because they involve kind of the same parameters being ordered. So if you look at Wi-Fi, for instance, often at this point in the lecture I go through some numbers on Wi-Fi so you get a feel for it. I think it's probably not a good use of time given where we're at in the semester. But if you look at Wi-Fi is frequency selective fading, okay, because you just measure the time it takes for signals to finish propagating around the interior of the building compared to the sampling rate, which is like 20 megahertz or so in Wi-Fi. You don't end up with impulse response like this. So you have ISI, and that's hence OFDM. That's why OFDM is used in Wi-Fi. Wi-Fi signals or channels are underspread, and then whether it's slow or fast kind of depends on what you're doing. Okay, if you're doing like telephony and walking around pretty quickly, it could be slow. Sorry, I have that backwards. Anyway, depending on what you're doing and whether you're moving and stuff, it could be either fast or slow. Okay, so that's the classification. We can need kind of one more background bit before we can start talking about how to communicate over wireless channels, and that's what we call statistical fading models. So essentially, we need a distribution for the channel impulse response. Okay, the reason is that, like, when you go to build a wireless communication system, you need to quantify the performance, and the performance tends to, in practice, it depends on the chance that the channel just really aggressively filters one frequency. Okay, like your error probability can be controlled by that event. And so if you want to talk about error probability on your system, you need to quantify what's the chance that the channel filters one frequency really aggressively. Okay, so you need a probability distribution on the H, effectively. For ComCloud, we didn't need this. Okay, although H was not really known exactly at design time, its variability somehow was never such that we had to talk about the probability we get this H or that H or whatever. So we could just kind of dodge the whole issue of how to model that thing stochastically. In wireless, you can't dodge it. Okay, you need a stochastic model for the H. Okay, so I say models because there are lots of models people have proposed. I'll just show you one that's most prominent, and it's the one we'll use. It's called Rayleigh fading. Rayleigh fading. Okay, if the impulse response in discrete time is such that the individual coefficients in the frequency response can be modeled as strictly symmetric Gaussian, zero mean, and some variance that depends on the sample. Okay. Rayleigh fading does not specify the dependence among the samples. Okay, it doesn't say how the first, the zero sample of the impulse response depends on the first one. That's unspecified. It just says marginally each of these things we model this way. Marginally, we model them as strictly symmetric, complex Gaussian. Okay, so why would we do that? I mean, that's certainly mathematically convenient. But why is that a reasonable model? So the justification people usually give for this is the following. So if you remember the formula we had for the discrete time impulse response in terms of the continuous time impulse response and other stuff, it was like this, right? So you had sum over paths. You have a path gain for each path. Okay, you have a phasor that comes about from the mixing in frequency up and down combined with the path delay. Okay, and then you have the reconstruction pulse at the DAC. And then this is ft minus, n minus f tau I minus f tau, I believe, right? So this is the formula we had in the modeling section for the discrete time impulse response at one particular time. Okay, so So here's the argument. I can model this thing by this distribution. So let's suppose there are a lot of terms in the sum, so many paths, okay? Then, each term in the sum, a priori, I don't really know what the delay is going to be, what the gain is, and so on. But because these paths represent like different, because the terms represent different physical paths, they're kind of like uncoupled from each other and therefore independent. And so it's like I'm adding up like a bunch of random independent things, and each of which has kind of a uniform phase to it, okay, because of this term here. So by essential limit theorem argument, maybe you could model this by that, okay? This is kind of iffy, all right? If you're in what they call a rich fading environment where you have like a really large number of paths, some kind of indoor thing with a lot of reflections, maybe this would be reasonable. For outdoor cellular, where the number of paths is relatively few, it's like how many mountains do you have around you, like you don't tend to have very many terms in this sum, so this is kind of specious, I think. But anyway, this is the model that people use, and that's the justification they normally give. Okay, so this is a bit questionable. So like any results you get from this model, you should bear in mind that like this link right here is a bit tenuous. Okay, and so any results you get that are like really dependent on this particular assumption, you should maybe be a bit skeptical of. Okay, but that said, most of the results you get aren't really that sensitive to this assumption. If you replace this with another distribution that's kind of similar, you get sort of similar results. So it doesn't really matter on some level. But anyway, that's the distribution that people tend to use. And this is the justification. It's essential limit theorem argument. OK. And sometimes, you can vary the the sigmas. You can vary these. So you have one be really large and then the other ones be small to kind of capture the fact that you have like one line of sight path that's strong and a bunch of reflections. So there's some parameters you can pick. OK. So that's background. So I think we're ready to start talking about how to communicate over these channels, unless there are any questions on the classification. Are we good on that? OK. So let's talk about communicating over these channels. And like I said, there's no one-size-fits-all solution to this. It depends on what kind of channel you've got. So we're going to start with slow, flat. It's always underspread in this class, OK? But you can do slow or fast, flat or frequency selective. So we have 4 possibilities. We're going to start with slow, flat. OK, a priori, that seems like the easiest and like the most desirable case to have. OK. In fact, somewhat surprisingly, it's like the worst one of the 4 to have. It's the one you really don't want to have for somewhat surprising reasons, and I'll show you that right now. So let's start with slow, flat, fading channels or wireless channels. OK. So the channel model would be Y. Because it's flat, there's no ISI. And because it's slow, the channel gain is not changing. So your channel mix looks like that. Okay? Flat implies diagonal. Slow implies all the diagonal entries are the same. Okay, there's no time variation in the gains. Plus noise. Okay. The noise vector, we'll assume is I d circularly symmetric Gaussian. The H we're also going to assume is circularly symmetric Gaussian. That's Rayleigh fading. That will normalize to have variance 1. So if that weren't the case, you could just take your Y at the receiver and just divide it through by normalization factor to get these to have variance 1. So that's without loss of generality. And we have a power constraint, of course. Like that. All right, now since H is random, like you got to be careful about what's known about it and who knows what about it. Okay, so when you treat H as just like deterministic, then you just generally assume it's kind of known to everyone. Yeah.
Is that one realization of H for every channel, or is it a different realization per sample?
For different realizations over different samples or channels? Samples, yes. It's one realization of H for the entire, for all the samples. Yeah, so this is the slow assumption. So it's like, this is the duration of communication. This is like your 100 milliseconds window here, okay? And the slow assumption is that the channel is not changing over that window. So whatever realization of H you get, you're stuck with it for the entire duration, okay? Because you can't like wait it out, because you got this delay constraint that kind of forces you to communicate over just n samples and no more. Yeah, other questions? Okay, so how do we communicate over this? Let's suppose, let's start simple. Suppose we send, or more precisely try to send, 1 bit per sample. Okay, so just encode 1 bit in each of these samples, decode them separately. I should finish my point here. So since H is random here, you have to specify kind of what knows, what's known about it and who knows what about it. We're going to assume for right now that the realization of H is known. So H is random, okay, but the realization of H is handed to both the encoder and the decoder, okay? In reality, of course, there's no genie that just hands you that information. You got to figure it out. Okay, you got to send probing signals through, measure, feedback, and so on. For a slow fading channel, it's not an unreasonable assumption, okay, because the channel is varying very slowly. Okay, so you can send some probing signals through, measure it, and get back. In any event, we'll assume H, the realization of H, is known to both the encoder and the decoder. Okay. So let's just focus on one sample alone then. If we're studying 1 bit over each sample, we just have like, n decoupled problems here. So let's let U be the bit that we're sending. Okay, our channel for one sample is going to be y equals h x plus z. And the natural scheme is to just do antipodal. Send that 1 bit over that one sample. Okay, so for the encoder, you probably pick plus or minus square root of p, depending on the value of u. Okay. One subtlety here is that, bear in mind, in this channel, x does not have to be real. Okay, it can be purely real, but it's not constrained to be purely real. Okay, so I wrote this here. This is probably the most natural way of writing it, but you could put like plus j square root of p minus j square root of p. Okay, you'll get the same overall performance. Okay, if you just take the x signal points I've selected here and just kind of rotate them in the complex plane, okay, that'll make no difference. Okay. Okay. So for the decoder, we need to find the map ML detector. So it's possible to just treat this as a kind of generic map ML problem. Treat the real and imaginary components as like 2 real components in a vector, and you just have detecting 1 bit in or detecting a vector with 2 uniform possibilities in the presence of Gaussian noise. So you can work all that through. I can show you a trick though that simplifies the calculation a lot. So for deriving the map ML detector, one trick is to define y prime to be h star over its modulus y. Okay, assuming h is not 0, in which case you can't really divide by it, so this makes no sense. Assuming h is not 0, okay, then this is a completely invertible transformation, right? I can get y back from y prime. So I haven't lost anything. Okay, in terms of x and z, y prime is going to be h star h over h modulus x plus h star z over h modulus, right? And this is going to be h modulus squared. That'll cancel one of those. So I'll get h modulus x plus h star z over h modulus, right? Okay, let's define this to be z prime. Tell me about the distribution of z prime. Yeah.
Circularly symmetrical.
Yes. Okay, the reason is just write this as modulus of h times a phasor. Okay. The moduluses cancel. You just have phasor times z. And I guess we're using the fact that the channel is kind of independent of the noise. So this didn't really come up in the ComCloud thing because we were taking h to be deterministic. But once h is random, you got to specify the joint distribution between these two things, right? So it's natural to assume this is independent, right? I mean, this is a function of like path reflections. This is a function of like thermal noise in your receiver. So these are statistically decoupled processes. Okay. So I've reduced the channel to that. All right, let me split this into real and imaginary components. So if you're the decoder, you effectively have two real numbers at your disposal now, right? You have the real and imaginary part of y prime. Modulus of h is real, x is real, right? So that is in the real equation, but not in the imaginary part. So if I take imaginary part, this is all going to fall out. I'll get just imaginary part of z prime, right? All right, now observe if you're the decoder and you're trying to detect x, okay, this scalar here is completely useless, right? It has no signal in it, just noise. And furthermore, the noise is independent of the noise in the information-bearing signal, right? So this is like, you know, someone hands you useful information, and then someone just on the side like flips a coin and tells you the value of that coin. Like that extra coin flip is just useless. Okay? So the channel effectively becomes this. Okay? And that is just a like antipodal signaling scheme over the reals. So the two possible received signals, if there's no noise, is the channel gain plus or minus square root of p. And you have like standard deviation square root of n over 2 Gaussian noise superimposed on top of that. Okay, and the map ML decoder will just threshold at 0. So just take real part of y prime, which is real part of h star y over modulus of h. Okay, and if that's bigger than 0, then guess we're saying a 1. If it's less than 0, then guess we're saying a 0. You can also drive all this just through a minimum distance test. Okay, just stack the real and imaginary components from the original problem to create a two-dimensional real vector. Apply minimum distance rule, simplify. Okay, you'll reduce to this. What about the error probability? Okay, so the error probability, you can get errors depending on both what the noise does and what the channel gain does, right? So h is random for us. It's known, but it's random. And there's also the noise, okay? And those two things kind of work in concert to create errors. So we'll first find the error probability conditioning on the channel gain. Okay, and then we'll average over the possibilities for h to get the overall error probability. Okay, so later we'll average. just going to write it like this: probability of error given the realization of H. All right, so this we can just write down because it's like an antipodal problem, right? So it's the chance that the noise is strong enough to push you the distance from this signaling point to 0, right? To your decoding threshold, right? Chance of the noise strong enough to push me from here to here. Okay, so that's going to be a Q function. I have the distance that we need to deviate normalized by the standard deviation of the noise. I guess maybe I should put little h here because we're conditioning on the channel gain being little h. Okay, so this is going to be 2 times modulus of h squared times the SNR, all in the square root, Q function. Yeah? Okay. So now we need to average this over h. So the overall error probability, PE, would be this thing averaged over h. So I'll write it like this. This looks like a mess, right? So let's talk a bit about the Rayleigh distribution. Actually, maybe I should have said this when we used the Rayleigh fading. So you can show a couple things. If you define V to be modulus of h squared, okay, then you can show V is exponential with mean sigma squared over 2, I guess. Or just 1, I guess. Because the h was h was circularly symmetric complex Gaussian with variance 1, right? So this is just going to be e to the minus v. E is greater than 0, 0 otherwise. And if W is just the modulus of H, then it has PDF, let's see, 2W e to the minus W squared. If W equals 0, 0 otherwise. I have that written down. Let me double check this. Yeah, I think that's right. Okay. Does this look familiar? I have a circularly symmetric complex Gaussian random variable. I look at the PDF of its modulus and its modulus squared. Okay, and the claim the PDF of the modulus squared is exponential. The PDF of the modulus itself is this. Look familiar? Yeah? I see some people nodding. Where have we seen this before? Yeah? Homework 1, yes. One of the problems in homework 1 is to say, it wasn't phrased quite this way because we didn't have circularly symmetric complex Gaussian random variables, but if you look up your homework 1, okay, it was take basically a circularly symmetric complex Gaussian random variable, look at its modulus squared and its modulus, find the density, okay? And that's why that problem was there, right? For this reason, okay? I don't like to waste homework problems, so that was there as a plant for this. This, by the way, is called the Rayleigh distribution. That's where this fading gets its name. It's a Rayleigh distribution. Okay, so applying that here, okay, if you want the overall error probability, okay, we've got to take this expression, which is a function of h, okay, plug in the q function, which is defined as this tail integral, right? Okay, and then integrate this against, depending on how you parameterize it, one of these two densities, integrate the whole thing, okay, which, to me sounds like just a messy calculation is going to lead nowhere. Okay, you plot it in MATLAB, you get some plots, okay, that's what I would guess would happen. In fact, this has a really clean answer. Okay, so you can show this equals 1/2, 1 minus square root of SNR over 1 plus SNR. It's just like that. Does that look familiar? Time's of the essence here. Don't hold back. It's what? Homework 8, yeah. So turns out it has a nice clean answer. It's not hard actually. You get two integrals here. You have one for the expectation because you're integrating against one of the densities. I recommend doing the exponential density. So just write this as v here in place of h squared integrated over v. Okay. So you have two integrals, one for v, one for the q function. You just swap them and go. Okay, and this pops out. Okay, so this actually has a nice answer. So there's the error probability. To get an intuitive feel for this, we're going to look at the high SNR regime. Okay, and again, you can debate, how practically reasonable that is. Wireless systems tend not to be like super high SNR, but just to get an intuitive feel for it, let's suppose the SNR grows. So we're in the high SNR regime. Okay, in that case, the error probability, as SNR tends to infinity, this whole thing's going to behave like 1. So you get 1 minus 1 is 0. So the whole thing's going to 0, but at what rate? If you just do a Taylor series approximation to square root of x over 1 plus x as x goes to infinity, okay, you'll see this error probability behaves like 1 over 4 times the SNR. Okay, so I'm not going to do all that. I'm sure you can do a Taylor series approximation. Just do a Taylor series approximation to this thing as a function of SNR. Okay, and you'll get that at high SNR, this error probability goes to 0 as 1 over 4 SNR. What do you think? Is that good news? Bad news? Do you like? No? Why not?
Diversity's 1.
Okay, we haven't. Yeah, diversity is kind of like the punchline that we're driving toward here, but I have not said anything about diversity yet. So this it goes in the right direction. As you increase SNR, the error probability goes down, so that's happy news, right? That's a sanity check, I guess. But it goes to 0 with SNR extremely slowly, okay, compared to what we're used to. Okay, so compare. Suppose the h it wasn't random, it was just locked at 1. Okay. Rather being Sukhi's measure complex Gaussian with, variance 1, suppose you just lock it so that the modulus square is exactly equal to 1 rather than being equal to 1 in expectation. Okay? So in that case, this averaging does nothing. Okay? And the error probability is just q of square root of 2 times SNR in the square root, right? And q function is approximately e to the argument squared, right? So 2 SNR. So that's what we're used to. When we did ComCloud, these are the sorts of calculations we would do. Okay, the error probably goes to 0 exponentially in the SNR, right? Here, 1 over the SNR. Okay, there's a world of difference between this and this. Okay, this goes to 0 extremely fast compared to this one. Okay, so if you run some quick numbers, okay, if you want the error probability to be 10 to the minus 6, if h is 1, Then the SNR has to be, it's like 13, I think. I'm going to cheat and look this up here. 13.8 or 12 dB. It's reasonable. But if you have this random fading, okay, so like, you know, if you use this model to model the chance that you get destructive interference at the receive antenna and these different paths come in and just like cancel each other and you end up with a really weak H, okay, if you account for that in your model, then your error probability is like this. So the SNR needs to be 250,000, right, to give me 1 over a million. Or, and that's like 50 dB or something, 53 dB. Yeah, good luck with that. Okay, that's not going to happen. I think I mentioned with Wi-Fi, it's like, you know, if you put things like the laptop and the Wi-Fi next to each other, you get SNRs of maybe like 40 dB or something. That's like, you know, the best you're going to get. Wi-Fi adapts its data rate depending on what the SNR is, and I think it maxes out at like 3 dB. So beyond that, you get no improved data rate because the design decision was that this is not going to happen in practice, so why bother? Okay, and the reason SNRs are so low, I mean, you know, this is totally reasonable for ComCloud, right? ComCloud is actually like, you know, at least if you don't artificially constrain the power, it's more like 100 dB, right? And there's a very simple physical reason that I think it's important to keep in mind why wireless channels have such low SNRs, like well below this. Okay, and this is because most of the transmit energy ends up being wasted in the wireless realm. Okay, in ComCloud, most of the energy that comes out of the headphone jack on the transmit PC will make it to the receiver. Okay, the filter does not attenuate very much. Okay, it's largely just like an R. It's largely just an L and a C with some little bit of R. Okay, so most of the energy travels through. On the wireless side, most of the transmit energy is lost. There's a homework problem on this fact for homework 8. I intend it to be a very kind of simple-minded, like high school geometry type of problem. I guess some people are thinking about like these like antenna transmission formulas and stuff. I was not thinking that. Okay, it's more like the calculation I was intending to do on that problem was just estimate in a typical scenario how far is a cellular base station from someone using their cell phone. So you need to like go on the internet and try to get a sense of what that number would be. Okay, you can bring up maps of like, you know, where the cell towers are in Ithaca and just kind of get a rough order of magnitude number for that. Okay, and then assume the base station is using an omnidirectional antenna, so all the energy just kind of like is spread out uniformly over the sphere that propagates outward. Okay, so this constant energy is spread uniformly over the surface of that sphere. It propagates outward until eventually it's at the radius of the distance to the handheld receiver. And then just think about what fraction, like what solid angle of the whole sphere is taken up by the little handheld, right? So like this has like an effective little antenna aperture, which is kind of governed by the geometry of this thing. Okay, and if I'm whatever, a kilometer away from the base station, okay, what fraction of the solid angle of the sphere centered at the base station with radius up to this point is this area here taking up? It's going to be small, right? Okay, and the moral is that the vast majority of the energy is completely wasted. It's going off in random directions that we don't want. Okay, so I mean, this speaks to like directionality would be really useful, right? And you know, it's that's a whole other topic. But if you're not doing that, then you know, most of the energy will be wasted. So your SNRs end up being really low just because so much of the energy is going off into space. Okay. There's a useful way of thinking about why you get this versus this in terms of dominant error events. Okay, so let me show you this. This is like just an intuitive explanation for why we get this number. Okay, so we did the rigorous math. You get this number. Okay, next I'll show you like a heuristic way of understanding why you get this number here that's useful for understanding how to try to get around this. Okay, so the topic is deep fades. So let me put the picture back up. So this picture with the 2 signal points. And you have like Gaussian noise blurring the received points, right? Okay, so nature picks an H. That's a function of your of the path gains and the path delays and so on, right? So you have various paths, and they sort of superimpose to give you an H. And if they're destructively interfering, you'll get like an H with a small magnitude. If they're constructively interfering, you'll get an H with a big magnitude. So where these points are, how spaced out they are or spread apart they are, depends on H, which depends on kind of the ray tracing geometry of the situation. Okay, the spread here is a function of the thermal noise in the receiver, so that's kind of fixed. Okay. Observe if the H is such that like these 2 pulses end up close together, then you're going to tend to have an error. Okay, in particular, if H, modulus of H square root of P, were less than, like in an order of magnitude sense, the standard deviation of the noise, then errors are likely, right? Okay, if your channel, so these are all capital letters, but this is supposed to be a random variable. This is fixed, that's my power level. This is fixed, that's the noise level. Okay, so this is like deterministic, so this is the only thing that's random here. Okay, so the message is if the channel gain is too weak, namely below this, okay, then when you go to plot this thing, these 2 curves are going to have a lot of overlap, okay, because the gap between them is on the same order as the standard deviation of this noise. Okay, so it's very easy then for the noise to kind of push you from one signal point to the other. Okay, so if the channel gain is too weak, the noise can easily cause errors. And what is the chance of that happening? Chance of this event occurring? All right, I'm going to square it because I like to work with exponential distribution instead of the Rayleigh distribution. So just square everything, get modulus of H squared, P, n over 2. So we have that, right? H is exponential. Or sorry, H modulus squared is exponential, mean 1, right? So this event has this probability. Yeah? This is the exponential PDF over this range. Okay, in the highest in our regime, this is a small number. So it's close to 0. When you're close to 0, this integram is like 1. So that's just approximated by 1. One over 2 SNR. Very close to the number we got here. This simple-minded calculation here almost gave us the right answer. It's only off by a factor of 2. Pretty good, right? In particular, this explains why you're not going to get something like this. Okay? So in fact, you can show the dominant way. We haven't really shown this here, but you can show the dominant way that an error occurs in this channel, okay, is that you're in what they call a deep fade. So this is what they call a deep fade. This event here is a deep fade. Like fading is when you get destructive interference, and then a deep fade is when the destructive interference is so strong it just annihilates the signal completely. Okay, and you can show, we have not really shown it here, but you can show the dominant way errors occur is that you're in a deep fade. The dominant way you get an error is that the H here, okay, is so small that it's easy for the noise to push you back and forth. Okay, you don't tend to have errors where H is big and somehow this thermal noise was like extremely atypically large and somehow it it pushes you from here all the way to here. Okay, you're fighting the Q function tail in that kind of event, so that's not the way things tend to happen. It tends to be the deep fade, and that kills you. Okay. So we're sending 1 bit over 1 sample. We're getting an error probability that, at least at a normal SNR, okay, is going to be too high. The error probability is too high. So what can we do? This is a good recap of like many ideas we've discussed in this class. What do? You can try repetition coding, right? Let's back off the rate. We're sending 1 bit per sample, so our data rate is exactly the sampling rate. The error probability is too big, so let's back off from the data rate. See what happens. So we'll say try repetition coding. So suppose we have 1 bit, and we send you using 2 samples. Okay, so our channel model is you have y0, y1. Those are the 2 samples that comprise the output of the channel. Both samples experience the same gain. That's slow fading, right? This is not changing over time, or at least over the course of our transmission is not changing. X, Z. Okay, the noise is the usual business. H, same as before. Power constraint, same as before. And now we're going to send 1 bit over these 2 samples. Okay, so x0 and x1 are going to be equal. And they reach that same antipodal signaling input as before. Okay, so just repeat, before we were sending 1 bit over 1 sample, so now just grab a second sample and just send the same thing over that second sample. All right, so you can analyze the map ML decoder for this. You can analyze the error probability for this. It's pretty standard bread and butter stuff for us at this point. I'm not going to go through the whole calculation because it'll use up a good chunk of the rest of the class period. And I think hopefully you all are comfortable doing that kind of calculation now. If not, okay, just divide everything in the real and imaginary component, create a big vector problem, and just apply the map ML stuff we did back in September. That's how to go about doing it. So I'll just tell you the answer. As SNR tends to infinity, the error probability goes to 0 as 1 over 4 SNR, as opposed to 1 over 2 SNR. We've gained a factor of 2 in the error probability. Maybe a bit surprising. Definitely bad news. Okay, definitely bad news. Okay, because if this was too big with a factor of 2, like dividing by a factor of 2 rarely fixes your problem. Okay, if the error probability you were getting was like, I don't know, 1 in 100, you need 10 to the minus 6 or something, a factor of 2 is not going to save you. Okay, and in general, if we send over L samples, the error probability in the high SNR regime is like 1 over 2L times the SNR. Can you read that? 2L SNR. So that's pretty pessimistic. I mean, just to give you a sense of like how bad this is, it's Suppose you want an error probability target of 10 to the minus 6. And suppose the SNR you've got is 1. Okay, that's totally within the realm of possibility. Okay, the power and the noise are on the same order of magnitude. And you want, a small error probability. Okay, so your L, it's got to be, if you ignore the 2, it's like 1 over the error probability, right? So 1,000,000. Okay, so your data rate is 1/1,000,000th of the sample rate. Okay, so what is the Wi-Fi bandwidth? Wi-Fi sampling rate? I mentioned it earlier today. Anybody know? Okay, it varies. There's a couple of options, but order of magnitude? Is what? It's what? That's the carrier. The sampling rate is kind of the bandwidth around the carrier, which has got to be a lot lower. Yeah. It's 20 megahertz, yes. There's actually, I think there's also a 40 megahertz, option, basically 20 megahertz, right? Okay, so you do this, use 1,000,000 samples with repetition coding. You're not getting a data rate of 20 million bits per second. You're not getting 200,000 bits per second. You're getting 20 bits per second, right? With this angle or with this approach, right? So you're probably better off just taking the data, just putting it on a USB stick and just walking it over, rather than trying to mess with all this repetition idea. And you can do like convolutional codes or whatever instead of repetition coding. There are more sophisticated ways of doing it, but they're not really going to save you. By the way, with the USB stick, like walking the data over, I actually have a serious point to make about that. Okay, so there was, when I started teaching at Cornell, circa 2006, someone did a study of Netflix. And at the time, Netflix was not really a streaming service. They just mailed you DVDs. Okay, do they still mail DVDs? Yeah, okay. You have to pay for it. Okay, so we always had to pay for that, but wait, you have to pay for the. You have to pay additionally. Okay. Anyway, they started out as just that's all they were doing was just mailing you DVDs. So someone looked at how many DVDs they were sending around, and they computed how many bit meters per year Netflix was providing. Okay, so how many how many bits are they moving over how many meters in a given year? Okay, we looked at the North American portion of the internet and looked at how many bit meters that was carrying per year. Okay, concluded that Netflix mailing DVDs through the US Postal Service was moving more bit meters per year than the entire North American portion of the internet. Okay, now that was like circa 2006. Obviously, that's in internet years, it's like dog years, right? In internet years, it's like a different era. Okay. But I mean, I was there. I can tell you. I mean, it didn't feel like radically different. I mean, most of the stuff you did in the internet now you could have done then. I mean, video streaming maybe wasn't quite at the same level, but so that might not be true now. Netflix probably mails fewer DVDs. The internet can carry a lot more data. Okay, but that was true then. Okay, so there's a moral to this story, which is like even as you learn all this fancy stuff, not just in this class. You go through all these classes, you learn all these fancy techniques and stuff. Like, don't lose your common sense. Okay, sometimes the best solution to your engineering problem literally is to like burn a bunch of DVDs and ship them. Okay, and like don't lose fact of that basic fact. Okay, and it's easy to lose sight of it when you immerse yourself in all this stuff. Another way of putting it is like never underestimate the bandwidth of a UPX truck full of DVDs. Right? I shared that line with one of my senior colleagues who's since retired. I'm actually in his former office, and I shared this line with him. I thought it was really clever. And he said, "Yeah." When I was, how did he put it? When I was in school, we used to say, never underestimate the bandwidth of a 747 full of tapes. So it's like the same concept, just different technology. Okay, but anyway, this is not really working for us. Okay, we need a better approach. And at this point, it's not really clear what the better approach is. I mean, you can do convolutional codes or whatnot. It doesn't really buy you a whole lot. It might just seem like these channels are just junk. Like you can't really communicate over them at the rates you'd want to achieve. Okay, and on some level that's true. There is a trick you can use by throwing money at the problem and adding hardware that solves this. Okay, and hopefully we'll have a brief period to talk about that on Thursday. But let's table that for a moment and move on to the other kinds of channels. Fundamentally, the problem here is that you go back to the deep fade. Okay, so when you have just one of these, it's like the dominant error event is that H is just really small. H is random. H is a function of what kind of interference you get among these different paths in your wireless channel. It can happen, they destructively interfere. severely. When they destructively interfere severely, H ends up being like near 0. Okay, or at least small enough that it's easy for the noise to just wreak havoc with your transmission, and then you're stuck. Okay, you can see why adding another channel, like another sample, doesn't really buy you much, right? Because if this is near 0, that's near 0. So what good is the second equation? You know, it's like I don't want more of equations with the same gain. I want some fresh gains. Okay, I want to roll the dice again with H is what I really need, not same H, roll the dice again with the noise. Okay, so let's go on to other types of channels. So next we'll do flat fast. Okay, so here's the picture to have. So this is time. Okay, so flat means no ISI, right? Fast means the channel's changing over the transmission. Okay, so your transmission is long enough, or it can be long enough. It's allowed to be long enough so that the channel actually changes over the course of the transmission. Okay, so you'd have a time period here where, like, the bit or a bit enters the encoder. Okay, and there's a time at which the bit must exit the decoder. Okay, and this is the delay spread right here. Okay, let's assume you have L coherence times. And of course, in practice, the coherence time is not like a really precisely defined quantity. It's kind of an order of magnitude notion. But anyway, let's assume you have several coherence times here. We'll say L. So coherence time 0. This is coherence time 1, coherence time 2, coherence time L minus 1. Okay, so you have L different coherence times. Okay, so the channel, you know, something's moving. Okay, that's where you get short coherence times in wireless systems. Something's moving. Transmitters are moving, receivers moving, reflectors are moving, everything's moving. Something's moving. Okay, okay, and this time period is the coherence time is the time period over which the channel H is roughly constant. Okay, so you start out, the channel's kind of constant, but then after this amount of time, it's changed on you because things are moving, and then after a while, more time, it's changed on you again, and so on. Okay. For now, we're going to model this as just like the channel is like completely constant over this band, and then it's like abruptly regenerates itself. And then it's constant for a band, and abruptly regenerates itself, and so on. Okay, that'll be our assumption for right now. That's obviously not the way real channels work, right? It would just sort of continuously kind of fluctuate, okay, and this is the time it takes before it, you know, fluctuates enough that you notice. Okay, but we're going to assume for right now it's just constant and then abruptly changes to a completely new independent realization. Constant for a while, then abruptly changes, and so on. Okay? Here's my favorite. Okay. Suppose we use one sample per coherence time. Okay, so I'm going to number my samples a little bit funky here. So x0 will be like the first sample in this coherence time. x1 will be the first sample in this coherence time, and so on. Then I'll have xl minus 1, which is the first sample in that coherence time. Okay, and what happens during the other samples in these coherence time, let's not worry about that. Okay, just leave them idle for right now. Okay, they don't exist. Okay, we're just going to think about communicating over, send one bit using the first sample from here and the first sample from here, and so on. Okay. So our channel model looks like the following. Okay, you'll get Y outputs. You get the output Y. There are L components to it, 0 through L minus 1. Okay, the channel gain, the channel matrix is going to be diagonal because it's flat fading. Okay, but because it's fast, okay, the gains are going to be different across these different samples. Because the gains are different across the different coherence times. Okay, so you'll get H0, H1 to HL minus 1. The input is x0, x1 through xl minus 1. And then you have the same noise as before. Okay. Let's talk about distributions. So the noise, the usual thing. Okay. The channel gains we'll assume are also IID, but we'll normalize it so that they have variance 1, like that. Okay, so in the slow fading case, all these gains were the same, right? Now in the fast fading case, I have different channel gains on the different samples. So we'll send 1 bit over these L samples. Okay. So U is our bit. I'm going to do repetition coding across those L samples. Okay, so I'm going to send the same bit, over each of these L coherence times. So X, 0, x1, all the components of x are going to be equal, plus minus square root of p. Again, these don't have to be real. Okay, you can put j square root of p minus j square root of p here. You'll get the same. I mean, the decoder will look a little bit differently because things will be rotated, but the error probability will be the same. I find it easier just said to be real, but it doesn't really matter. All right, let's do the map. ML decoder. So again, maybe we should make clear, we assume H is known. That's kind of important for this. So all these we assume are known. This is less reasonable of assumption than it was in the slow fading case because they're changing now, right? So, I guess we're kind of assuming at the beginning of each coherence time you send some probing signals, measure the channel, feed that back so everyone knows it. And then when the channel changes at the next coherence time, you got to do it all over again. Okay, so we're assuming that's happening in the background. Okay, and that's less reasonable of assumption here than it was in the slow fading case, okay, because the channel's changing on us, but we'll continue to make that assumption. Okay. I can write the channel in this case as y equals h times a scalar x plus z, right? Because all the x's are the same, right? So this vector here, okay, is like all plus square root of p or all minus square root of p. So just take one of these components of the vector, okay, just call it x, okay, and then you can write it this way. Actually, if you want to express it in terms of u, you can do that, right? 2u minus 1. Okay, so now we have a problem where we're trying to determine whether the signal is one of two possibilities. It's either plus, this is p, sorry, square root of p, not 2. It's either plus square root of ph or minus square root of ph. You're trying to detect where the signal is, which one of those two vectors it is. They're equally likely. Okay, you have IID Gaussian noise. It's kind of omnidirectional. Okay, so the optimum rule will be a minimum distance test. So just compare your receive vector to one of the transmit vectors and also the other. Okay, and go with the smaller. So if this is smaller, you'll guess that u was 1. And if this one was smaller, you'll guess that u was 0. All right, so you can simplify this by expanding it all out. You'll get y norm squared. You'll have minus y Hermitian h. With the square root of p, you'll get minus h Hermitian y with the square root of p. And you'll have plus p length of h squared. Expand the bottom one. Okay, you have length of h squared again. Now plus all of these cross terms. Like that. Okay, I just expanded this and this. We get a bunch of cancellations. Okay, at that point, you can cancel the square root of p, or the square root of p's can go. Okay, these are the same terms, so if you combine them, then what do we get? So we'll have 2 y Hermitian h plus 2 h Hermitian y. Comparing that against 0. Like that. Okay, this is a scalar, right? It's a complex scalar. So is this. They're complex conjugates of each other. Right? So this is the real part of one of them, and I can cancel the 2's. So you get real part of h Hermitian y. Threshold that with 0. Oops, that's not a matrix, it's a vector. No underline. Okay, so this generalizes our slow flat fading case where we sent 1 bit over 1 sample. If you choose L to be 1 here, this is just a scalar. Okay, and your rule is take the scalar gain, complex conjugate, times y scalar, take a real part of that, threshold with 0. Okay, so this recovers our earlier calculation in the slow flat fading case. Okay, so now that we have this, we can compute the error probability for a given h, then average over h. Okay, and we'll see that the time variation, although it kind of presents some problems in terms of learning the channel and stuff and making synchronization and training more complicated, kind of saves us from an error probability standpoint. Okay, because I'll leave it as a suspenseful point. Okay, so on Thursday we'll see why this error probability is so much better than it is in the slow flat fading case. And then we'll talk about frequency selective fading, and then with luck we'll loop back to slow fading and talk about how you might deal with a channel like that, and we'll be done. All right, I'll see you Thursday.